Welcome back, everyone. Today we're going to be going through some induction exercises that accompany section 1.2 of my textbook. So we're going to dive right in, and there's going to be 3 exercises we look at today, including one on the sum of odd numbers, the geometric series formula, and we're actually going to prove strong induction through the well-ordering principle. So before we begin, I want to do a brief reminder on the principle of induction, which again says suppose that we have a statement P that we wish to show is true for all positive integers at least 1, then we have to show both the base case and the inductive step in order to prove it. And we're going to see this with the first 2 exercises, but we're also going to prove them in 2 different ways as well. So the first exercise says prove that the sum of the first n positive odd integers is n squared. And to begin with this, whenever I have an example, I like to see some small cases. So we begin by proving the base case for small n. So we see that 1 is equal to 1 squared, 1 plus 3 is equal to 2 squared, and 1 plus 3 plus 5 is equal to 3 squared. So all of these work. And we can now make the inductive hypothesis and assume that it holds for n equals k. So therefore, we have 1 plus 3 plus 5 plus all the way up to 2k minus 1 is equal to k squared. And that's the inductive hypothesis. And then we have to show it holds for the next value. So we now add the next odd number to both sides of the hypothesis. And we get that the sum on the left here is exactly the same with the 2k plus 1 term, and the sum on the right is just k squared plus 2k plus 1. And you might recognize that now as just k plus 1 squared. So therefore, we have now shown that the identity holds for all positive integers n by induction, because we've shown that if it holds for n equals k, then it also holds for n is equal to k plus 1. Now let's look at a different way to prove this. So we could also let the sum be s equals 1 plus 3 plus 5 plus all the way up to 2n minus 1. And we can write the sum forward and backward to use symmetry, and this gives us s is equal to 1 plus 3 plus 5 plus all the way up to 2n minus 1, and we write it backwards, and notice that this column right here sums up to 2n, and so does this column, as does this one as well. All of the columns will sum up to 2n. And we have n terms total, so in total we're going to get 2s is equal to 2n n times. Well, that's just 2n squared. And then when we divide by 2 on both sides, we're going to get that s is equal to n squared as we found before. So we've now seen this identity in 2 different ways. We've seen it through proving it with induction and proving it using the arithmetic sequence method. Now let's look at a geometric series. So we want to prove the geometric series formula for all positive integers n, which says that 1 plus r squared plus all the way up to r to the n minus 1 is equal to r to the n minus 1 divided by r minus 1. And we begin with a small base case of n equals 1, and we get 1 on the left hand side, and we get r minus 1 divided by r minus 1, or just 1 on the right hand side, so it works. And we assume the geometric series formula holds for n equals k. Therefore, it holds that we have the left-hand side equals the right-hand side here, and that's the inductive hypothesis again. And we now add the next term to both sides of the hypothesis. And on the left-hand side, we're going to get the same exact thing as before, plus r to the k, and on the right-hand side, we're going to get plus r to the k. We can now write the right-hand side under a common denominator, and we're going to get r to the k minus 1 plus, well, r to the k plus 1 minus r to the k. And notice that the r to the k terms cancel there, so we get that it's just r to the k plus 1 minus 1 divided by r minus 1, which is exactly the identity for n equals k plus 1. So the geometric series formula therefore holds for all positive integers n by induction. I want to give you all the opportunity to actually try to prove this in a slightly different way. And I'm going to pause right here, and each time I pause, I'll pause for about 10 seconds, and I'll let you think through it. Feel free to pause the video as well, and please comment below if you have any ideas for how to prove this identity in a different way, and I'll give you various hints. So my first hint is let the sum be s equal to this sum as we saw before. What can you do to both sides of this equation to use symmetry? The second hint is consider multiplying both sides by the common ratio r. And now the final hint is consider the expression s times r minus s equals s times r minus 1, and see if you get a lot of terms that cancel. I hope that these hints helped you out with trying to solve this problem, and feel free to comment below with your solution. Now we're going to remind what strong induction is, and then we're going to prove strong induction from the well-ordering principle as well. So strong induction is exactly the same as normal induction with the base case, except the inductive step says assume that we have all of the previous dominoes being true. So P1 up to Pk are all true, and then we want to show that Pk plus 1 is also true. So for proving the strong induction principle from the well-ordering principle, we're going to use proof by contradiction. So we assume that the set S of all integers n such that P of n is false is non-empty. So therefore, by the well-ordering principle, there must be a least element of S, which we say is m. Observe that 1 is not in S, therefore m is greater than 1. And the reason for that is we've already shown the base case. Furthermore, since m is the smallest element of S, Pn is true for all 1 less than or equal to n less than or equal to m minus 1. But by the inductive step, we know that if P1 and P2 and P3 all the way up to Pm minus 1 are all true, then Pm is true as well. So hence Pm must also be true. So this contradicts the earlier assumption that Pm is false, so therefore we've arrived at a contradiction and the well-ordering principle proves strong induction. Stick around next time while we're going to be exploring the binomial theorem and binomial coefficients. I look forward to seeing you then.